Good afternoon to all. Welcome to the 12th week tutorial session of NPTEL course, Convective Heat Transfer. My name is Ananthakrishnan. I'm a Ph.D. scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. So this is the last week tutorial that is based on the miscellaneous topics that were discussed in the last week that were uploaded in the last week lectures in the website. So this is based on thermochromic liquid crystals, infrared thermography, and droplet evaporation and K epsilon turbulent model. So we'll see one problem that we didn't see in the last week for that K epsilon turbulent model. We can actually move into the problems. So look into it. So this is based on the effective emissivity that was discussed in this week's lecture. We need to determine the effective emissivity of a semi-transparent body when it is heated for a reflectivity of 0.2 and transmittivity of 0.2. This is not based on the spectral emissivity that we usually use, which is based on 1 minus of the transmittivity and 1 minus transmittivity minus reflectivity. Based on the Kirchhoff law that absorptivity is equal to emissivity, but this is slightly different. Look into it, and I will also try to solve it within a couple of minutes. So this is the case of a semi-transparent body, and consider it to be maybe a flat plate of plastic material. So when the plate is heated, the radiation generated within its volume must move away to the surface. The radiation which is actually produced within the volume must come out of the volume towards the surface. So this is like a plastic material, a semi-transparent body. So there will be several layers. So as and when the radiation comes out of it, it will actually reflect from every interface between different inner layers. So consider a semi-transparent body like a plastic, a non-metallic. So this should be a non-metallic semi-transparent body like plastic. So the radiation produced will reflect from the interface between different layers before reaching the surface. So every layer will be having its own reflectivity uh, and the transmittivity. So the radiation which is reflected back is then partially absorbed within the same volume, and the rest of it moves out of it. So as and when the reflection part actually gets reduced as and when it reaches the outside surface, but the reflection that happens within the different layers must be added up. So this is not a metallic semi-transparent body. So this can be expressed in terms of a geometrical series, and but we can use from the geometrical series we can arrive at the concise form of emissivity of the material of a semi-transparent body that will take into account the reflectivity as well as the transmittivity of overall spectral emissivity and the transmittivity. But this is somewhat different from that of a metallic body which is semi-transparent. In that case, we could have used the spectral emissivity as 1 minus of transmittivity, spectral transmittivity minus the spectral reflectivity. But for non-metallic semi-transparent body, this takes in the form of a geometric series, and we can arrive at the spectral emissivity as a function of the reflectivity and the transmittivity by this form. So given these two are 0.2, this will be 0.8 multiplied by 0.8 divided by 0.16. It will be 0.64 divided by 0.84. The spectral emissivity will be given as 0.64 divided by 0.84, 0.76. But if you have taken directly 0.2 and 0.2 for the metallic body, it would have arrived at a emissivity of 0.6. So that is a difference for a non-metallic semi-transparent body. If this becomes an opaque body, then the transmittivity part will be 0. Then only the reflectivity comes into picture. So if the transmittivity, if you put it to 0, then the original equation of the emissivity will be equal to 1 minus of reflectivity, which is same as that of a opaque metallic body as well. look into the second problem. So this problem is regarding the heat transfer that happens that occurs between the surface as well as the ambient. So this, though the question says that there is an infrared camera that detects a wall temperature of 22 degrees Celsius and the surface emissivity of 0.85. The ambient temperature is measured as 10. Calculate the rate of heat transfer, heat loss per square meter of hole. So this has got nothing to do with the infrared camera as such. It's basically heat transfer problem. We need to find the actual heat transfer that occurs from the wall to the surface. So it's a straightforward problem. We can use the Stefan-Boltzmann solution, Stefan-Boltzmann equation or law. Using Stefan-Boltzmann law, Q is equal to epsilon sigma epsilon T raised to 4 minus T ambient raised to 4. So we need to find the flux actually. That's why we can denote it by Q double dash. So sigma Boltzmann constant 1 meters per Kelvin raised to 4. Epsilon is given as 0.85, and the ambient can be considered to be like a black body. And since the wall is a small body compared to that of the ambient, the epsilon, the emissivity of the ambient can be taken to be 1. This is 295 raised to 4 minus 283 raised to 4. So we get it to be 0.85 into 5.77 10 power minus 8 divided by 1.225 into 10 power 9, and solving this we get it to be equal to 59.59, somewhere around 59 uh, 0.08 watt per meter square. So that is the heat flux or the heat loss per square meter from wall. It's a straightforward problem that has taken the Stefan's Boltzmann to calculate the heat transfer loss from the surface. So the previous week's lectures actually deals with the detection of temperature using infrared thermoscopy. In that case, infrared thermography. In that case, they have considered the heat transfer that occurs from the surface to that of the infrared camera, and they have actually used a correlation to actually relate this heat transfer to that of the voltage. So the voltage will be the output, and you input certain parameters, and you'll actually get the temperature of the surface. So in that case, you need to know a lot of other things that was discussed in the lectures. Look into the third problem. So this is actually a theoretical problem basically. Uh, and Consider a spray nozzle in the gas turbine engine, injecting droplets of size 50 micrometers into the highly turbulent flow. Velocity is approximately 80 meters per second. If the diffusion coefficient of the droplet increases, what happens to the Peclet number? So this is a straightforward problem. For this we should know what is Peclet number. The Peclet number is a dimensionless number that characterizes the relative importance of convective transport to the diffusive transport. So Peclet number can be defined as the dimension. Peclet number is the dimensionless number that characterizes the relative importance of convective transport to the diffusive transport. Peclet number can be defined as the Reynolds number multiplied by Prandtl number for the thermal case. Similarly, Peclet number for the diffusion mass transfer case can be defined as a Reynolds number multiplied by Schmidt number. So the Reynolds number is defined as U into characteristic length divided by kinematic viscosity. Prandtl number is actually the ratio of the momentum diffusivity to the thermal diffusivity. Similarly, the mass for the mass Peclet number can be defined as UL divided by nu multiplied by Schmidt number will be the momentum diffusivity to the mass diffusivity. So this is given as UL divided by alpha, and this is given as UL divided by D. D is the diffusion coefficient. This is the momentum diffusivity to the thermal diffusivity, the mass diffusivity diffusion coefficient. So it actually this Schmidt number and Prandtl number actually kind of in the physical sense they mean that it's kind of relative importance of the momentum, the hydrodynamic boundary layer to the thermal boundary layer in the case of the Prandtl number, and in the case of Schmidt number, it's hydrodynamic boundary layer to the concentration gradient or the mass transfer boundary layer. So in our case, it's a diffusion coefficient. It's a mass transfer problem. We are asked what happens to the Peclet number once the diffusion coefficient increases. So it's an inverse relationship. As a basically it's a ratio of the convective transport to the diffusive transport. Once the diffusion coefficient increases, Peclet number reduces. It's an inverse relation. So as D increases, Peclet number decreases. It's a straightforward. Look into the fourth problem. So this is a problem based on uh, sessile droplet evaporation under mixed mode. So among the following, which actually represent the sessile droplet evaporation under mixed mode, only constant angle, constant radius, both constant angle and constant radius, none of this. So before going into it, we need to actually understand what is a droplet evaporation modes. So which all are the modes that are there for the case of droplet evaporation basically. There are droplet evaporation has got three modes. First is constant contact radius, CCR. Second is a constant contact angle, CCA. And third is a mixed mode. So in the case of constant contact radius CCR method, the contact portion radius remains the same, but the contact angle keeps on varying during the evaporation. So initially the contact angle will be this much. As and when the contact, as and when the fluid evaporates, the contact angle reduces. So here, constant contact radius. So this is the RC, constant contact radius, but the contact angle reduces with evaporation. Second one is constant contact angle. In that case, in order to maintain the same contact angle, the contact radius keep on reducing. So the originally, just like the first case, this would have been the contact radius, and this is the contact angle. In order to maintain the same contact angle with evaporation, the contact radius keep on reducing. So this is the final. In order to maintain the same contact angle, so this is the theta 1, theta theta 1, theta 2. Theta 2 is less than theta 1. Here theta 1 equal to theta 2. This is theta 2. This is R con R1. This is R1 final. It will be R2. So in order to maintain a constant contact angle, the contact radius reduces. This is half of this is the radius. So R2 is less than R1. In the mixed mode, both contact angle and the contact radius reduces. It's a combination of the first and two. That is the mixed mode of sessile droplet evaporation. This is immobile, where the droplet is constant on the is stationary on the surface. That is sessile droplet evaporation. Mixed mode. So if this was the original case, the new case would be somewhere like this. Both R2 is less than R1, as well as theta 2 will be less than theta 1. Theta 2, theta 1, R1 and R2. So this is a mixed mode. So that solves the problem. It's both contact angle and contact radius. bo- here both of them decreases. Even the following which represent the mode of sessile droplet evaporation under mixed mode operation. So both contact and the contact angle and the radius decreases. So option 3 is the correct answer. So if you try to plot it, the ratio of the contact radius to the original contact radius, as well as the new theta contact angle to the original theta angle with respect to time. So what we could observe is that there will be initial stage where there will be a constant contact radius phase. Then there will be a phase of constant contact angle, and then there will be a mixed phase. So the first phase will be constant contact radius phase, where the if you try to observe, this is 0 to 1 and 0 to 1. So the first phase will be a constant contact radius phase. So you can expect this to be somewhere close to horizontal. So that is the constant contact radius phase. Then there will be a constant contact angle phase where you expect the radius to go down. And then there is a last phase where uh, there will be mixed phase. So this is the constant contact radius, and then there is constant contact angle, and then there is a mixed phase. So this is the uh, R versus RCO ratio. Similarly, theta versus theta zero ratio will be somewhat different. Initially, it will be constant contact radius. There will be a variation in the radius, and then it will somewhat be a constant, and then it follow a similar trend as that of this. So this is a constant contact angle will be having almost a constant. Theta will be almost a constant through that phase. Then the mixed phase comes where both of them decreases. So in our case, this is the region where we operate, where the mixed mode operation happens much later in time. Okay, now we can move to the next problem. Look into it. So in this case, the constant K equal to 0.02 is given, and water droplet has an initial diameter of 2 mm, and it evaporates in a still environment at a rate defined by this constant, and we need to calculate the diameter of the droplet after 10 seconds. So for the case of point droplet approximation, we can actually use the law called D squared law, where the surface area of the droplet can be assumed to be the rate at which the surface area decreases can be assumed to be a constant. So for small time interval, we can assume we can integrate this particular equation, and based on this constant, we can arrive at the value. So integrating this for small time intervals, we'll get D, uh, final D as a function of K and the time difference. So in this case, it will be, I beg your pardon, it's a negative K. So D new time, D squared minus D original divided by delta T is equal to minus K delta T. Therefore, D squared is equal to D minus K into delta T. So the new diameter D is equal to root of D minus K delta T squared. So the original diameter was 2 mm. So it will 4 squared minus 0.02 into 10. That will be 0.2. So it's 2 squared, I think. 2 squared, 4 minus 0.2, it's 3.8. It will be equal to 1.95 mm. So that will be the diameter of the droplet after 10 seconds based on this D squared law. So so much assumptions have come into picture once we use the D squared law. Uh, uh, there is a spherical symmetry where the forced and natural convections are neglected, and there is no spray effect. Diffusion rate is being controlled. It's a constant pressure process and constant gas transport properties, quasi steadiness in this process. So all these assumptions are taken into account, making it slightly inaccurate, but it will give an initial approximation of the diameter of the diameter if you know the value of the K, the constant that decides the evaporation. So that will be a variable based on the ambient condition as well as the process in which the evaporation takes place. So basically this constant is nothing but minus of uh, d squared divided by dt, and from there we integrate and find this value. It's a straightforward problem. Look into the sixth problem. So this is a case of a turbulent flow K epsilon model. A flow with a velocity of 10 meter per second and kinematic viscosity is passing over a flat plate of length 2 meters. We want to calculate the turbulence kinetic energy and the dissipation rate using the K epsilon model. So the velocity u is given. Straightforward problem which uses the standard definitions of turbulent intensity as well as the dissipation rate. So u is equal to 10 meter per second. Kinematic viscosity is 10 power minus 6 meters square per second. Length is given as 2 meters. Turbulent intensity is normally for the external flow, it will be somewhere around 5%. External flows. So we'll use these values to calculate the turbulence kinetic energy and the dissipation rate. So we calculate the turbulence kinetic energy. K. It's given by the formula 3 by 2 intensity squared into a velocity squared. Straightforward intensity is 0.05 squared and the velocity average mean velocity is 10 squared. So the value will be 0.375 meters square per second. So that will be the turbulent kinetic energy. And the second portion is we need to calculate the dissipation rate. Epsilon. So based on the turbulence kinetic energy and the constants that we could use for the experimentally empirically determined constants and the length, we can determine the value of the dissipation rate. So the dissipation rate epsilon is equal to the constant raised to 3 by 4 k raised to 3 by 2 L power minus 1. So this is normally 0.09 for the epsilon model problem, and k is given as 0.375. We determined it the turbulence kinetic energy, and length L of the plate it is 2. So we use it straight away. So the value will be coming around 0.00233 meters squared per second cube. That is the dissipation rate of the turbulence kinetic energy. So this is straightforward problem which makes use of the formulas that are available to calculate the turbulence kinetic energy and the dissipation rate. Look into the seventh problem. How does the thermochromic liquid crystal respond to different temperatures and what will be the color of the emitted radiation? So this is a theoretical problem. Uh, in the case of thermochromic liquid crystals, the incoming light waves reflect of nearby crystals and are together by a process called interference. The color of the reflected light depends on how closely the crystals are together. When we heat up or cool down the liquid, we'll change the spacing between them or push them into a different phase, altering the amount of interference that happens between the different emitted radiations from the different layers. The liquid crystals, it will look a different color depending upon what temperature they are, because changes in temperature make them move closer or further apart. For example, if I try to draw it, if the material is hotter, so the liquid crystals will be closer to each other. But when they are far away from each other, in the case of cold, so liquid crystals will be far away from each other, and this will be having an effect on uh, the the light which is emitted out of it. So in this case, it will be a hot. It will emit blue reflected light. In the case of a cold material, it will emit a red reflected light. So in the case of a cold one, the emitted light will be more towards the red side. In the case of a hotter one, the emitted side will be more towards the blue side. So the liquid crystal, when it is hotter, the crystals will be more close towards each other, but when it is colder, it will be far away from each other. And the emitted radiation will be of different color, as we have mentioned. Look into the eighth problem. So the question states an electrical light bulb for the outdoors is approximated well by a sphere with a diameter of 6 centimeters. It is being swept by a 2 meter per second wind and its surface temperature is 60 degrees Celsius. The air temperature is 10 degrees Celsius. Calculate the rate of forced convection heat transfer from the outer surface of the light bulb to the atmosphere. So this is the case of forced convection, but we do not know whether this is a laminar flow or a turbulent flow. For that, we need to calculate the Reynolds number. First of all, we calculate the properties, air properties. Air temperature is 10 degrees Celsius. It's a constant wall temperature and constant free stream temperature. So we calculate the air properties, the dynamic viscosity at this temperature of film temperature kind 2 into 10 power minus 5. For the so in this case, mu nearby the wall can be of this one, and far away at 10 degrees Celsius, it will be 1.76 into 10 power minus 5 kilogram per second meter. Similarly, the uh, far away from the string, the kinematic viscosity is 0.144 centimeter per second. Thermal conductivity is 0.025 watt per meter Kelvin. Prandtl number infinity is equal to 0.72. So we first calculate the Reynolds number that is equal to u infinity t divided by mu infinity. That is u infinity is 2. This is 0.06. 36 centimeter. That is a characteristic length, and mu infinity is 0.141 into 10 power minus 4. So the Reynolds number, this is 8511. So the Reynolds number is given as 8511. But till now, we do not have a standard correlation for the spherical objects that are being hung in air stream. So in this case, this is an air light bulb for the outdoors with swept by the air like this. We do not know what will be the transition in the case. We know for the flat plate, but we do not know for the case of these bulbs what will be the transition. So Whittaker proposed a correlation. Proposed a correlation for Nusselt number, average Nusselt number. So the correlation states nu d bar is 2 plus 0.4 Reynolds number raised to 1 by 2, 0.06 Reynolds number raised to 2 by 3, Prandtl number raised to 0.4. mu infinity by mu1 minus 1 by 4. So this has been tested for Prandtl number between 0.71 to 380, 3.5 Reynolds number as low as 3.5 to 7.6 into 10 power 4, and mu infinity by mu w less than 3.2. So in this case, we evaluate all the physical properties at the surface temperature, at the free stream temperature T infinity, except the value of mu w. This is nearby the surface temperature. So this is quite different because we are not using a standard correlation, but this is an empirical correlation that is suitable for this range uh, based on few set of experiments conducted for the spherical objects rather than an analytical correlation. So we can calculate the Nusselt number value based on this. Nu d bar is equal to, that's why we initially calculated this as W and infinity, all the properties. 0.4 into Reynolds number is 8511 raised to 1 by 2 plus 0.06 8511 raised to 2 by 3. Prandtl number is 0.72 raised to 0.4 mu infinity by mu 1.676 raised to 2 raised to 1 by 4. So this value Nusselt number is given as 54.58. So, but if you closely observe the Nusselt number correlation, when no flow is the condition, if you closely observe, for no flow, Reynolds number Re will be equal to 0, and in this case, Nusselt number will become equal to 2. So this represents a pure conduction case for steady radial conduction between the spherical surface and the motionless medium that is surrounding it. So this is the steady state conduction. So in this case, we could see that Nusselt number is very much greater than 2. That means that there is heat transfer due to convection that happens. And this is the case of from this correlation, we can't actually predict whether this is a turbulent or laminar case, but we can, for the time being, since the correlation is valid for this much of a Reynolds number, we can, for the time being, take it to be valid, so that we can substitute the Reynolds number straightforward. Then we can, this question says we have to determine the rate of forced convection heat transfer from the outside surface. So for that, we need to calculate the heat transfer coefficient. The heat transfer coefficient will be given as Nusselt number into K infinity divided by D is 54.58 into 0.025 divided by 0.06 equal to 22.74 watt per meter square Kelvin. So once you determine the heat transfer coefficient straightforward, the heat transfer that occurs between the question says we have to determine the heat transfer, convection heat transfer, forced convection heat transfer that occurs from the outside surface to the ambient, to the atmosphere. So the heat transfer is given by H into area into T surface minus T infinity, or T volt minus T infinity. This is given as 60 and this is given as 10 and this is 22.74. We can calculate area that is equal to outside area, that is 4 pi r squared or pi d squared, that is pi into 0.06 the whole square, 0.0113 meters squared. Therefore, Q is equal to, substituting this value, we'll get to 12.85 watt. So this equation, though in the previous case of the flat plate, we have considered Reynolds number, and that is used as a constraint, that is used as a condition logical statement. If that is less than the critical transition Reynolds number, you'll take the laminar heat transfer correlations. If not, you take the turbulent. But here, this correlation that we have used for the spherical flow over a sphere, that is valid for laminar and turbulent, but the constraint is the Reynolds number range that is considered. So if our Reynolds number falls between this range, this is actually valid, that we can use it straight away without checking whether this is laminar or turbulent. And the heat transfer coefficient, the heat transfer that occurs between the ambient and uses of the range of 10 watts, somewhere around that. So that's also a set of problems that we had for this week. We'll just have a brief overview of what we have seen this week. The main questions we have discussed were from the miscellaneous topics: the infrared thermography, thermochromic liquid crystals, droplet evaporation, K epsilon turbulent model. The first question was based on the effective emissivity of a non-metallic semi-transparent body like plastic. So in this case, there will be multiple layers, and every layer will be having the emissivity, absorptivity, and the transmittivity. Taking a geometric series, we will get the effective emissivity of the body in terms of the reflectivity and the transmittivity. Normally, if it was a metallic body, a semi-transparent metallic body, you could have directly taken a single, there will not be multiple layers. You could have straight taken a single equation of 1 minus of transmittivity minus reflectivity to get the emissivity. But in the case of metallic semi-transparent body of non-metallic material, we have to go for this correlation, this equation, which is which takes into account the geometric progression of the reflectivity. So the reflective amount of radiation that is reflected will actually get reduced as it moves outward towards the surface. Based on that, we arrive at this equation. So if it was a transparent metallic body, if semi-transparent metallic body, the emissivity would have been 0.6, but here it is 0.76. That takes into account the progressive reduction in the radiation, a reflection of the radiation that happens. And the second one, it's a straightforward problem. We have to actually determine the heat loss through radiation. We use the Stefan-Boltzmann law to calculate that based on the emissivity given and the temperature that is given. So this has got nothing to do with the infrared camera, the energy balance on the surface of the infrared camera that we have seen in the lecture. This is a straightforward problem to determine the heat transfer that occurs between the surface as well as the ambient. The third one was a theoretical problem that deals with the diffusion coefficient and the Peclet number. So basic formula, Peclet number is actually inverse of the diffusion. It's actually shows it's a dimensionless number which shows the strength of conversion to diffusion. So in that way, the diffusion coefficient, the diffusion reduces with respect to increase in the Peclet number and vice versa. Fourth was based on the droplet evaporation, stationary sessile droplet evaporation under mixed mode. So we have seen the conditions when the mixed mode will get operated. That happens at a higher time from the starting point. So initially there will be constant contact radius problems. Then as and when time increases, it will become constant angle, and then to the mixed mode. So in the mixed mode, both the contact angle as well as the contact radius reduces. The sixth one, yeah, it is based on the D squared law for the droplet evaporation. So basically, D squared law says that the area reduction with respect to time of a spherical droplet. For that, several constraints are there, conditions are there that I had discussed. So for that to valid, this is directly proportional to the evaporation constant that depends upon the conditions. So here it is directly given. So we just use integration to find the value of the new diameter. So then we have seen a problem that we didn't discuss in the last weeks to calculate the kinetic and turbulence kinetic energy and the dissipation rate using the K epsilon model. These are standard equations that are derived based on the intensity as well as the velocity to determine the turbulent kinetic energy and the MC, the dissipation rate of the turbulence kinetic energy, not the specific dissipation rate omega. It's a standard dissipation rate is given based on the turbulence kinetic energy, the length as well as the C mu, that is a constant, empirical constant for the K epsilon model. We saw a problem on the thermochromic liquid crystals, how the temperature variation affects the thermochemical chromic liquid crystal and the radiation that comes out of it. And finally, we saw a problem on the spherical, the flow over a sphere. For that, the heat transfer coefficient is actually determined from a Nusselt number correlation that is empirically determined rather than analytically determined. So it uses this range of the Reynolds number. If the Reynolds number of the current problem falls within, we can use it straightforward, and from that we determine the actual heat transfer that occurs between the spherical surface as well as the ambient. That completes the session for this week. In the next session, that will be the final session, we will actually have a recap of all the lectures that we have seen, all the tutorial sessions we had over the past 12 weeks, and we will discuss few topics, few problems based on the important topics that we couldn't cover till now. That's all. Thank you for this session. We'll meet tomorrow.